I'm going to present the work called Optimal Allocation of vBBUs Considering Processing Power and Distance Between MDC and RH in Fog runs. Dr. Da Silva is with Virginia Tech, United States, Connect and Trinity College Dublin, Ireland. Dr. Bolt is with Unicinos University, Brazil. Me, Dr. Ralha, and Dr. Morota are with the University of Brasilia, Brazil. Here's the outline of this presentation. First, I'm going to give a brief introduction to contextualize our work, followed by the system model definition and problem formulation. Then I will present the use case we developed to evaluate our proposal, followed by the results we obtained. And finally, I will present the conclusions and future work. An F-run is the result of the application of fog computing to a C-run. The F-run inherits components and aspects from C-run centralized architecture, such as the baseband unit pool that processes the workload from distributed remote radio heads. F-runs extends the processing to the edge by using micro data centers placed alongside to the RAN, which turns a typical RH into a fog RH, or fog access point. So the F-run balances the centralization and distribution of computational resources. There are several open challenges related to F-runs, such as edge caching, processing consumption minimization, RH and user equipment assignments, and virtual baseband unit allocation. In particular, this work focuses on the problem of vBBU allocation, in which the use case is based on the fact that application service providers, ASPs, are interested in offering service in the cloud and also in the edge of the network, aiming to achieve low latency and improve the user's quality of service. So optimal allocation of vBBUs can reduce the operator's expenditures and can also increase the operator's income by leasing idle resources to ASPs. The contributions of this work include a model to formulate the problem of vBBU allocation for cost minimization while considering the distance between MDC and RH, the evaluation of the gains in terms of minimal processing power in use, considering different scenarios based on a real demand dataset. So the system model. We consider an F-run composed of a set of MDCs from macro cells and from small cells. Each MDC has several processors for different classes of vBBUs that are responsible for remote processing of the workload of RRHs from macro cells and also from small cells, in which both are serving the user equipment. The different classes of vBBUs within MDCs have different specifications for processing power, efficiency, number of cores, and cost of allocation. From Morota et al., we get the minimum number of processors required to process the workload for each RH for each time slot as a function of the distance between RHs and MDCs, which is presented in this equation 1, where phi is the delay budget according to the technology in use, h stands for the distance for signal regeneration, which determines the number of hops required, lambda stands for the delay per hop, and c is the speed of light. In this work, we aim to optimize the operator's allocation decisions in order to minimize the cost by deciding how to best assign the RHs to MDCs. To do so, we formulate the problem as a binary integer linear programming problem, in which the objective function, the equation 2, aims to minimize the sum of the system's vBBU allocation cost. This objective function is subject to 3 constraints. The first constraint is for horizontal allocation. We use it to ensure that an MDC must be able to process all the assigned workload, which is important to restrict the vBBU allocation according to the available computational power. The second constraint is for vertical allocation, used to ensure that the processing power required to compute the workload must be less than or equal to the available processing power within RAN's MDCs, considering all the vBBU classes and the RRHs. These constraints takes into account the distance between RHs and MDCs. The last constraint is to ensure the assignment of all RHs workloads to at least one MDC, ensuring that all the workloads in the run are going to be processed. So the decision variable for this optimization problem is binary. It will be equals 1 if there is an assignment between MDC and RH, or 0 otherwise. So to evaluate our work, we employed the Milano CDR dataset in our experiments. This is a real telecommunications dataset from Telecom Italia with several features, including internet traffic for 2 months in the city of Milan. In order to apply this dataset, we faced some challenges, such as how to adapt this dataset to a 3GPP simulation, how to separate the different regions, and how to represent the traffic behavior for these regions. So this figure presents a heat map for normalized internet traffic activity, considering the entire dataset, separated by weekday and weekend, considering data from 2 weeks. For our simulations, we selected the data that belongs to the region around the city center Milan, which is the region with the highest traffic activity. After pre-processing and filtering the data, we applied k-means clustering to separate the different behaviors of each region. We clustered the data in order to discriminate the internet traffic behavior among the regions in different periods of the day. Then we divide the map into 5 clusters with different demand behavior during a day. These bar plots show the demand behavior for each cluster, presenting the normalized value of the internet traffic for each cluster on weekdays and weekends. To evaluate our proposed solution, we simulated an F1 system according to a scenario described by 3GPP, where each macrosite is composed of 1 macrocell and with 1 MDC and 1 cluster of small cells with an MDC positioning in the centroid of this cluster, a cluster with 4 small cells RHs. This figure illustrates how we divide the simulation of Milan city center into four smaller simulations, with characteristics from downtown, urban, suburban, and sub-rural. For simulation of downtown region, the distance between macrocells are set to 1 kilometer. For urban, 2 kilometers. For suburban, 3 kilometers. And for sub-rural, 9 kilometers. For each simulation, the behavior of the RHs in each macrosite is described following the behavior of each cluster, such as illustrated in this figure. Before I present the results we obtained, it's important to present some definitions. First, the total number of cores for each time slot, which is the total number of cores for the entire F1. Next is the number of idle cores for each time slot, which is given by subtracting the total number of cores by the number of allocated cores at each time slot. Next, the cost of allocation at each time slot, which is the sum of the cost of allocation to serve the run at each time slot. And lastly, the maximum income for each time slot, which is obtained by multiplying the number of idle cores by a constant defined by the operator, which represents the price of leasing. In our experiments, we define this constant as a half of the price of allocation charged by Amazon for 1 core of SC5 instance. This figure illustrates the influence of distance between MDCs and RHs on the minimal number of vBBU per class that are allocated, in which characterizes an important trade-off in F1s. It's possible to note that the number of processors required increases as the distance increases. To evaluate our solution, we focused on the analysis of potential gains with an optimal allocation of vBBUs, which is achieved by applying binary integer linear programming. We combine these results with the possibility of increasing the operator's income by leasing idle resources. These figures summarize the results we obtained, separated by region types, date types, and periods of the day. Also, these figures present the proportion of maximum income per cost of allocation, indicating the potential of gains for network operators. The potential for gain is more relevant when the proportion is more than 1, which means that operator's maximum income is higher than the budget used to serve its demand. For these results, it's possible to notice that the maximum potential for gain from leasing idle processing power occurs during the night. It's also possible to notice that the gain is slightly higher for small cells on weekdays, and for weekends is more balanced between macro cells and small cells. For the remaining periods of the days, the most relevant results are from weekday mornings and afternoons for the urban region, and from weekday mornings to evenings for downtown. These regions and periods are the ones with the highest peaks of activity, and potentially the periods that ASPs are most interested in provisioning their service at the edge. These results show that there is a better opportunity for operators to increase their income through edge processing leasing in different scenarios, especially in downtown regions. So in this work, we investigated the opportunities for network operators to reduce their expenditures through optimal allocation of vBBUs. The results are highlighted the opportunity for network operators to exploit their infrastructure better and increase their gains by optimally allocating vBBUs and leasing idle resources to ASPs. In this context, we identified which situations this opportunity can be better exploited. As future work, we aim to incorporate migration and ASP transactions to our model in order to minimize the cost of allocation while considering the migration cost and also considering the potential of income gains by leasing idle resources. Also, we aim to use this baseline to compare different machine learning techniques used for vBBU allocation decisions. Thank you all for attending to my presentation.